brief description on how you were able to get the stiffness matrix of a quadrilateral element. So let's try to go in detail, starting from the principle of virtual displacement. So hopefully you have already an idea what a principle of virtual displacement is, and let's try to bring that forward for a quadrilateral element. Again, we're also going to discuss the different parameters that are required to be able to get that stiffness matrix for a quadrilateral element. So, let's begin. Now,
quadrilateral elements.
so we did spend some time trying to look into skeletal structures wherein our elements are 1D. So we just looked into truss or bar element, and then move on to a beam element. So we were able now to know how to derive the stiffness matrix for each of these elements. Now for 1D, we are able to get the symbolic form of stiffness matrix, but for 2D elements and higher, it will be difficult, if not impossible, to get a symbolic form for the stiffness matrix, so we have to perform a numerical integration. So what is that? We're going to learn later. So now I would like to go back again, let's start from the principle of virtual displacement and determining the different parameters that we need, Jacobian, straight displacement equation or matrix, and so on and so forth. Okay, so let's do this one slowly. So if we have our element, which is a quadrilateral element, so we can have this one, so any shape. So this can be any shape, quadrilateral element. You can have even a triangle, actually this method can work. So this one here, say for example, we have node 1, node 2, node 3, and node 4. Say for example, this is your element 1, and this is for your x1, x2 axis, or xy axis. So we want to know what will be the stiffness matrix for this element. Of course, we know that F equal to K multiplied by U. That's the general equation for finite element. So how are we going to solve this one here? So let's look at the element constitutive equation, F equal to K multiplied by U. So how do we get an expression out of that? We know F is equal to K multiplied by U, but what is K? We know that F and U are boundary conditions. So how do we derive K? How do we derive an equation for K in the first place? You have tried Galerkin's method or method of weighted residual. That's one method. And the other method is the principle of virtual displacement. So using the method of weighted residual, we can do that, but it's a more complicated solution. The easiest way is to use the principle of virtual displacement. So let's do that. So you have your principle of virtual displacement. You have your equation. Again, I'm just trying to write now this one without too much explanation. You have your forced vector. Let's have it there. So this one will be a transpose, wherein this one will be an 8 by 8 matrix. Why is that an 1 by 8? So why 8 parameters in the first place? So this one is x1, x2, so you have a u1, u2 for each of these nodes. So you have 8 displacement, 8 forces. So you will be expecting a stiffness matrix of 8 by 8. Yes? So just imagine a 2D bar, just about that. So a bar, we have a displacement along its axis, x1. But for this one here, a simple 2D element, very simple. Okay? What's more simpler than this one will be a triangle. But we can solve that triangle using this method here. Yes? So we have now your virtual displacement. So let's just put it there. So this one is an 8 by 1. So take note, if you have this one here, 1 by 8, 8 by 1, it becomes a 1 by 1, a scalar value. So force is equal to force multiplied by the distance, that is the work done. This is to be multiplied by the strain energy, or this one is equal to, the strain energy. So work done is equal to the strain energy. So you have your stress, 3 stresses, sigma x, sigma y, and sigma xy. Sigma 1, sigma 2, or sigma 1, 1, sigma 2, 2, sigma 1, 2. So 3 stresses that are involved here. So we have this one to be 1 by 3, that's the transpose. And then we have now your virtual strain. So since we have 3 parameters for stress, sigma 1, 1, sigma 2, 2, and sigma 1, 2, 2 normal, 1 shear, you have now also 3 strains corresponding to your stress. So this one will be 3 by 1 dV. So if you try to look at this one, work done minus this strain energy is equal to 0. So they are the same. So take note here that we can represent this virtual strain later with an 8 by 8 identity matrix. So although this one is 8 by 1, we can represent this one to be an identity matrix 8 by 8. Okay, so what do we intend to do here? Knowing that F equal to K multiplied by U, we need to find an expression for K. So I'm just going to write what we need to expect from this one here. So your equation for finite element will be this one here. Is equal to your stiffness matrix 8 by 8 multiplied by your displacement, which is 8 by 1. So from this equation, we're going to derive this one. And then these ones are your boundary conditions, very straightforward. So we need an expression for this one. So we are expecting, just going to write, so we were able to expect this one 8 by 8. And then we have this one to be the volume integral of your strain displacement. Okay, so I'm just writing this equation now, 3 by 8 dV. So this is what we want to, or this is what we're going to take from this one. Starting from this one, we will get an expression of this one, and then we will be able to get an expression for your stiffness matrix to be this one here. So let's just write the things that we already know. So of course, if you use the plane stress and plane strain assumption, you will get an equation for your stiffness matrix. So either you can use your plane stress or plane strain. Sorry, that's E. So either you use plane strain or plane stress, or plane strain assumption. So again, our question now is, how do we get this these? So okay. So the thing here is we are in the x1 and x2 plane. We can get an expression for this one just simply basing on the x1, x2. That is for hand calculation, but if you want to be more computationally efficient, then you have to do a mapping here. So from x1, x2 to c1, c2. That's why we do that, because we want to be efficient, because this one is a numerical method. We want the computer to solve it for us. Of course, nobody's preventing us from doing the hand calculation, but you probably don't want to do this one for each element. So you probably want to just have one black box there that you put in all your, what do you call this one, your locations, 1, 2, 3, and 4, and then it will solve for you, rather than doing or calculating a stiffness matrix for each individual element. So that's the purpose why we do a mapping. So let's continue with your PVD. So still, I'm with the PVD. So this one is your force, 1/8. And I have this one to be my, say let me have this one as UJ, just not to conflict, 8/1. And then I have this one to be my stress. So I'm just rewriting values here now. dV. So this one, your stress will be equal to, what is your stress? Stress will be equal to, if this is a 3/1, so this one will be E, which is a 3/3, your stiffness matrix. And then, sorry, Young's modulus matrix, or stiffness multiplied by your strain, 3/1. So we can substitute this one to this one later. Yes, what about your virtual strain? Of course, we will know that that will be dependent on your virtual displacement. So I can now put this one here. So I will have now my force transpose 1/8. I have now my U virtual displacement 8/1. So this one is a scalar value. So as you can see, this one is also scalar, 1/1, both scalar, the same. I can now have this one to be the volume integral of, let me just follow this, let me just use E outside, since this one is transpose. This one will be here, transpose, so it becomes a 1/3. And this E here will be a transpose value as well, because we're looking at the transpose of the stress. And then you have now your, so 3/3 there, virtual displacement 3/1 dV. Okay? So have a look. So the next thing we want to know, well, this one here is a virtual displacement. We can change this one later, or substitute a 8/8 identity matrix. So the question now is this one and this one. What is your strain, which is 1/3? So here, since we're looking at 2D, if you can recall a bar, just recall a bar. Your strain is equal to du dx, yes? for a quadrilateral element, your strain, because we have now x1 and x2, your strain will be partial derivative of u with respect to x, where x can be x1, x2. So we know that your u is n transpose multiplied by that ui. So if we're going to substitute this one here, we will have your strain 3 by 1 to be equal to partial of n with respect to x. This one will be a 3 by 8. And your ui, which is an 8 by 1. So this partial derivative of that shape function or geometric shape function with respect to x is equal to your strain displacement matrix, which is your, sorry, that's A transpose there. E transpose 3 by 8. Then you have now here your ui 8 by 1. Yes. Okay, so we have this one here, virtual displacement. If we were able to get this strain to be your strain displacement matrix transpose multiplied by your displacement, then we can actually get an expression for this one. So this one now, your virtual displacement will be the same. B transpose, which is a 3 by 8, multiplied by your virtual displacement, which is an 8 by 1. But like I said, we can substitute an 8 by 8 identity matrix here. Yes? So have a look. This, that, we got this one already. We got an expression for this one. This one is, we have an expression. So this one we can simply have a plane stress or a plane strain. Well, of course, this one is that B multiplied by your virtual displacement. So this is B multiplied by your displacement, while this virtual will be B multiplied by that virtual displacement. Yes? So what else do we need? This we know, this we know, this we know. So we can just simply substitute the expressions that we obtained. Yeah, let's do that. So I have now here my force, which is a 1 by 8. I have my virtual displacement, 8 by 1. So this one now is the volume integral of that strain displacement matrix transpose, which is a 3 by 8. And then I have now my, okay, so I'm just looking at this one here, ui transpose. Sorry, that is a strain. Sorry, this is strain. This one is 8 by 1. Let me. So this one here, I'm following this one here. Strain transpose. So our strain here will be B transpose UI, and then I take the transpose of this one. Yes? Because my strain is this one here, and then I take the transpose. That's why I have it there. So I can multiply this one with my E, 3 by 3, transpose. And then I can multiply this one with my virtual strain, wherein I got an expression for that earlier. So this one will be B transpose 3 by 8. And then this is to be multiplied by my virtual displacement. That will be 8 by 1. Yes? And then dV. There you go. So your strain displacement multiplied by your strain displacement transpose, displacement, take the transpose multiplied by your E transpose, and then strain displacement transpose multiplied by your virtual displacement. Yes, so please have a look. This one is 3 by 1, 3 by 3, 3 by 1. So end up to be 1 by 1. This one is 1 by 1. So let's try to move on. So here we can replace now So let's replace your virtual displacement to an identity matrix which is 8 by 8. Yes? So I can now replace this one here. 8 by 8. What else? Here. I can replace that with an 8 by 8 identity matrix. So what I have now is that force transpose 1 by 8, and I have this one to be an 8 by 8 identity matrix. This is the volume integral of this B transpose 3 by 8. My displacement 8 by 1. Take the transpose of that. This is to be multiplied by your stiffness matrix, or sorry, stiffness only, modulus. And then this is to be multiplied by that B transpose, which is a 3 by 8. And then I multiply this one with an identity matrix 8 by 8 dV. Yes? So take note. So we have to note here that if we have this one here, so we have this force here, transpose 1 by 8, and we multiply it by an identity matrix 8 by 8. So meaning that this one is a diagonal matrix with values of 1. So this one will simply be equal to Fi transpose 1 by 8. Because take note, this is just 1 by 1, or 8 by 8, with all the diagonals equal to 1 and the other values 0. So, using a similar analogy, we have now your straight displacement matrix multiplied by an identity matrix 8 by 8. So this one will be simply a B transpose. Yes, 3 by 8. Any questions so far? So what do we have next? So we substitute the values here, but for this one, so this one now is 1 by 8. So we substitute this value here, but we bring this one first, and then bring this one second, and then this one last. So if you allow me to write this one now, I can have this one to be transpose. So I won't be writing the values now, or the size of the matrix. So I can have this one to be the volume integral of, let me have this one here, that B transpose there. I'll put in an E here, which is transpose, and then I'll put in this one here. Transpose dV. So again, similar to what we did earlier with a bar or a beam, you can inverse this one, but you're going to end up to have the same value. So if you're going to transpose the whole equation, you're going to end up with Fi volume integral of B E dt ui dv, volume integral. So I'm going to bring out this one so that you have now your force equal to the volume integral B E B transpose dV ui. So this one now is okay, so you have this one to be 8. So that is a 3 by 8, 8 by 3. So depends on how you look at it, 8 by 3. This one is 3 by 3. This one is 3 by 8. And this one is 8 by 1. So I'm a bit confused. So this will be, so what's the equation that we get there? So this one is 8 by 3. this will be 3 by 3, and this will be a 3 by 8. Yes, so this one will be your K, 8 by 8. And this one will be equal to the volume integral B, 8 by 3, E, 3 by 3, B transpose 3 by 8, dV. So you have now an 8 by 8 stiffness matrix. So your question now, once we have this one from the PVD, we want to know how do we solve for that strain displacement matrix. So we got now this equation. Our problem now is to be able to get this one, we need your B, strain displacement matrix. Yes, so we have done this one in bars already, so we can now proceed. Yes, so this is our expression. For a 2D element, we can have a unit thickness 1. We can just have T. So we can simplify this one. Instead of a volume integral, we can have an area integral. Since we have a unit thickness and we're just looking at the plate, so this one is B, E, B transpose, thickness, D, X1 or dA. So let me just put their dA first. So that this one will be delta X1, delta X2, B, E, so that's how you do it. So you have a double integration here. Yes? So instead of taking the or integrating twice because of this one here, we can map it so that instead of performing analytical integration, we can perform numerical integration. And that's one reason why you want to map. So let's have a look. How do you map this one here? So initially from X1, X2 axis, so that's node 1, node 1, node 2, node 3, and node 4. You can map this one. Let me remove that. So this one will be your C1 and C2 axis, where this one will be positive 1, negative 1, positive 1, negative 1. So this one will be negative 1, negative 1, which is 1, 2, 3, 4. 1, 2, 3, 4. This will be 1 minus 1. Your second node, this will be your third node. 1, 1. And this will be your fourth node, which is minus 1 and positive 1. So here, you're trying now to map from this one to this one. So what does that mean? We'll explain later. Because what happens is that when you perform integration later, it's simple. It's just putting in the coordinates for this 1, 2, 3, 4 points. So you will see how the computer will do this numerical integration with different assumptions, of course. So initially, with the mapping, we have now this one here, originally 8 by 8. I'm just going to write the equation B yes. So this one now will become integral from -1 to +1, -1 to +1. So we have now a definite value for this one. And then this one will be your B, E, B transpose. We have now your thickness. You have your Jacobian value, which is the number, just another number, DC1, DC2. So this is what happens when you do the mapping from initially this one to this one here. And we'll try to define each of these parameters as we go on. So you will see later, it looks complicated, but when you put in the numbers, it's just a procedure. So the process in deriving this equation is quite laborious, but the solution is really straightforward. Yes, still we have a problem. We need to get this strain displacement matrix. Thickness, it's a unit. You can have this one to be 1. Your Jacobian value, this is not the Jacobian matrix, just the Jacobian value. This one is the determinant of your Jacobian matrix. And then others, you can just use some numbers later. So we need to solve for this one here. But before we can do this one, we need your Jacobian matrix. Yes, we need a Jacobian matrix. So how do we solve for the Jacobian matrix? Okay, just hang on. We have a lot of vocabularies here. So we have a Jacobian matrix. Just hang on, we have more. Hang on in there. Previously we have your shape function with respect to your B is equal to your partial of m with respect to x. So by chain rule, we can have this one to be partial. Let's have this one to be still ni. This one is with respect to c, so this one will be k. Doesn't matter, you can use p or m or n. And then you have your c, k with respect to xj. Chain rule, yes? So you just added this one here, it's the same. So that your, let's take this one here, or let's take this one here, sorry. So that if we have this one here, or let me change that, let me put there now as J. So does it matter now? So if I have this one, I can just bring this one over there. So I have now my partial ni. Now this one now is partial x, k, doesn't matter. If you put in m and t, it's just a dummy variable. And then we have now here partial xk with respect to cj.
Hello?
So here you have this initial chain rule, but I wanted to determine this one here, so I just bring this one to the other side. So I have now here partial ni. Instead of using k, I just wanted to use j. So just be consistent with your subscript. So you have now partial ni with respect to xk, which is this one here, and then multiplied by partial xk with respect to cj. So I'm consistent. So this will be cancelled out later because this one is a dummy index, so I end up to be having a partial ni with respect to cj. So what will be the value of k? So your k will be from 1 to 2. So x1, x1, x2, x2 later. So let's try to determine that. So you have now your partial ni with respect to, let's have this one to be partial c1. So let's try to expand this one. This one will be partial ni with respect to x1, partial x1 with respect to c1 plus partial ni with respect to x2, partial x2 with respect to c1. Second, partial ni with respect to c2. So this one will be partial ni with respect to x1, partial x1 with respect to c2 plus partial ni with respect to x2, partial x2 with respect to c2. So we can write this one now in a matrix form, and we will be able to derive from this one your Jacobian matrix. Yes, so let's write it in a matrix form. How do we do that? So we have now this one to be partial ni with respect to c1, partial ni with respect to c2. Yes. And then I can have here partial ni with respect to x1, partial ni with respect to x2. So I will have here my Jacobian matrix. So partial x1 with respect to c1, partial x2 with respect to c2, partial, oh sorry, that's c1. Oh yeah, shall
สองวัน
1.
ชอบแบบ
Partial x1 with respect to c2, partial x2
วัน
with respect to
ไรดู
c2. Okay, so this one now will be my Jacobian matrix J. But since I want to determine this one, then I can just take the inverse multiplied by this one here. So I think this one will be understood better when we solve problems later.
อุ้ยอุ้ยอุ้ย
So finally, if I want to determine this one here, so I have now here the inverse of my Jacobian. Then I multiply this one with partial ni yes. So here, most likely I can have my Jacobian to be, say to make it simple, let's have it to be J11, J12, J21, J22, wherein J11 will be equal to that, J12 is equal to that, J21 is this, and J22 is this one. Yes? So copy and let's have a 10 minutes break. And let's try to solve some. Let's try to discuss how you can get all these values.